I'd like to talk to you today about language models and relational models of the multiplicative additive Lambek calculus. And it's a pleasure to acknowledge joint work with Max Kanovich and Stepan Kuznetsov. Let's start with just a very simple example. So sigma is going to be a finite alphabet, and sigma plus the set of all non-empty words over sigma. Power set of sigma plus is the set of all formal languages over sigma without the empty word. And now there are several interesting algebraic operations. First of all, the multiplication, which is just if you have a set of words A and a set of words B, then you can look at just concatenations of A followed by U followed by V. Left division, we'll read this as A under B, consists of all non-empty words U, such that for every word V in A, V followed by U is in B. And similarly, the right division, B over A, is all those non-empty words U, such that for every V in A, U followed by V is in B. In addition to that, we have the usual operations of union and intersections, okay? And it's interesting to note that this relationship down at the bottom of the screen, the relationship between the divisions and the product. So that is to say that B is a subset of A under C, if and only if A times B is a subset of C. And in turn, this is if and only if A is a subset of C over B. Okay, so as the second example, let me look at relational algebras. This is another class of algebraic structures. Algebras of binary relations here. So let W be a non-empty set. Now let's fix a transitive binary relation U on W, which we'll call universal one. And we'll look at the power set, so the set of all subrelations of U, and we'll introduce very similar algebraic operations. Okay, so the multiplication now is just composition of relations. R under S is all those pairs Y, Z, and U, such that for every pair X, Y related by R, the pair XZ is related by S. The right division is defined similarly. And again, there are ordinary operations of union and intersection. And again, there's the same interesting relationship that S is a subset of R under T, if and only if R composed with S is a subset of T, if and only if R is a subset of T over S. Now, these are only two examples of a general algebraic structure called residuated lattice. It's a very old subject. I think it goes back to Krull in a paper in 1924, where he is investigating a theory of ideals in rings from an abstract point of view. And the residuated lattices were rediscovered independently in 1938 by Ward and Dilworth. There is a series of very interesting papers in Proceedings National Academy of Science and American Journal of Math. Just really very interesting work. People used to be interested in these things. Okay, so read the definition as I speak. I also like to turn your attention to this more recent book by Galatosh, Gibson, Kowalski, and Ono on residuated lattices and algebraic glimpse at substructural logics. Okay, so residuated lattices give algebraic semantics to substructural logics in a way that, for instance, hiding algebras give algebraic semantics for intuitionistic logic. Okay. And in fact, the logic of residuated lattices is the multiplicative additive Lambek calculus. With apologies to Professor Shikic, I'm going to do Gensen sequent calculus here. This is the ordinary stuff. One wonders why this had to wait for Lambek to discover it in 1958. It's just really Jensen sequent calculus with the proviso that the left hand now is a finite list rather than a finite set or a multiset. And there are two conditions which are strange from a logician's point of view. They were motivated by linguistic issues that Lambek was interested in. So the rule of the right introduction of the left division assumes that this context pi is non-empty. And similarly, in the introduction right rule for right division, what this does is ensures that if a sequent is provable, then the left-hand side is non-empty. And this is, as I said, important for linguistic motivations. In the semantics, this is the reason why we started with non-empty words in the formal languages example, in the linguistics example. Okay, so the cut rule is admissible. Algebraic models are residual lattices, and in particular, algebras of formal languages, my example 1, and relational algebras, example 2, I'm going to call L models and R models. Okay, of course, the modern view is that this can be viewed as a non-commutative version of intuitionistic linear logic, and this was investigated in detail by Abruzzi. I'd like to really acknowledge that work. Okay. Now, why did Lambek do this? He was interested in rules for describing natural language syntax. There's a very beautiful paper of his from 1958. And we can see this from the point of view of L models. All right. So for each letter A in sigma, the grammar associates one or more so-called syntactic types, which are actually formulas of the Lambek calculus. So let's say the letter A is associated to formula A. And then a word, A1 through AN, is considered grammatically correct. This is syntax. If the corresponding sequent is derivable. So the standard example is John loves Mary, and the corresponding sequent involves both the left division and the right division. Okay, so loves is a transitive word, and it gets this type. John is a noun phrase, Mary is a noun phrase. And you can amuse yourself during this talk or later during your walks in Dubrovnik or sitting and drinking your favorite drink of making a derivation of this and see how this works. Okay. All right, now again, I'd like to mention Professor Šikić because in his talk he mentioned distributivity. Okay, so I thought, oh well, how wonderful. Okay, I'll actually look at this in my talk. Okay, so of course both L models and R models turn out to be distributive as lattices. Okay, so this is exactly the distribution law that Professor Šikić was talking about. Okay, disjunction over conjunction. Okay, now of course in general residuated lattices can be non-distributive, and so the distributive law is not derivable in the calculus. And this is one of the things that prevents the calculus from being either L complete or R complete. Okay. Now, I want to turn your attention to a very interesting recent paper of Christian Worm, who came up with a very natural non-distributive modification of L models, which avoids this problem and gains completeness. There are a lot of partial completeness results. So what I'm going to denote as L conjunction, which for me is going to be the multiplicative additive Lambek calculus without the disjunction, okay, is known to be R complete, that is to say complete with respect to relational models. This is Andreka and Mikuláš, 1994. Now, the calculus without the disjunction and conjunction, that is to say, the multiplicative calculus, or in fact, the calculus as Lambek presented it, is L complete. It's one of the wonderful papers by Matti Pentus, this one from 1995. The calculus with only 3 connectives. So the fragment with only 3 connectives, left division, right division, and additive conjunction, is known to be L complete. This is Bushkovsky, 1982. And right away, we stumble on an open question. Okay, so take your L conjunction, which is known to be R complete. So there's no disjunction. Is it L complete? Sorry to say, still open after all these years. Okay, and it is also unknown what would happen if you just say, okay, well, so distributivity is messing you up. Why don't you just add it as an extra axiom? Do you get completeness? That's not known either. Okay. Okay, so the first thing I'd like to show today is that the situation with the calculus without conjunction is different from the situation without disjunction. Okay, so they're not symmetric. That's a surprise. So here's the theorem. This crazy sequent, don't even try to read it. The crazy sequent is not derivable in the fragment without conjunction, but it can be derived using distributivity axiom and cut. Okay, and therefore, unlike the fragment without disjunction, the fragment without conjunction is neither L complete nor R complete, because those two are distributed. Okay, so what the sequent is some kind of disjunctive encoding of distributivity. Okay, so how can you do this? Well, if you read all papers by Lambek and Pentus that I already mentioned, there is a so-called diamond lemma there. And the diamond, I'm not going to go into details, but the diamond lemma tells you how to simulate conjunction if you just have divisions and disjunction. Okay? And this is how our sequence arises. Okay? Now, if I had distributivity, then the simulation would, using cut, prove the sequent. Okay, now you might say, okay, so therefore it's not derivable. Now wait a minute. Okay, the non-derivability of our sequent in this fragment does not come automatically from non-derivability of the distributivity law, because the simulation is actually stronger than the conjunction. Okay, however, the derivability problem for this fragment is decidable, so we can just use derivability checking software, such as, for instance, that one developed by Gibson, which is available online, and I encourage you to play with it, which actually gives the answer in several seconds. In our conference paper in Volink 2019, and subsequently in the journal version in the information computation, which is available online, we also do manual proof search. And by the way, I'd like to mention you can also construct a clever small algebraic counter model, for that does require some creativity. Okay. Now, here's an interesting point. What about commutative and affine generalizations? Okay, so this is from Lambek calculus. What about intuitionistic linear logic? Okay, so let's add the permutation rule, okay, to the calculus, therefore making things commutative. And now we are talking about multiplicative additive fragment of intuitionistic linear logic. Okay, so that's one generalization. The other one is, in addition to that, let's add full weakening. Okay, and this will give us the multiplicative additive fragment of intuitionistic affine logic. Now it turns out that that very sequent, that crazy sequent, is still not derivable even in the presence of commutativity. That is to say, it's not derivable in intuitionistic linear logic. For the affine case, which has the weakening rule, the sequence has to be slightly modified, so you get another crazy sequence. So this counterexample is still there. Okay. All right, so this was the first adventure. Okay, now the second adventure is now let's add the unit. Okay, so in intuitionistic linear logic, the unit constant for multiplicative truth is axiomatized in the following well-known way. Okay, but observe that you have the empty left-hand side here. So therefore, if we want to deal with one, requires abolishing the non-emptiness restriction that we talked about before. Okay. In residuated lattices, in general, this corresponds to moving from arbitrary semigroups to monoids, okay, with respect to multiplication. And in particular, for L models, we're going to modify the definition of those algebraic operations by allowing the empty word in languages. Okay, and lo and behold, we get undecidability. Okay, so more precisely, the multiplicative unit constant one, you can see that is necessarily interpreted in L models as the singleton consisting of the empty word, and axiomatizing the unit as multiplicative truth would now yield interesting incomplete systems. So for instance, this equivalence is true in all L models, which now involve empty word, but not derivable in non-commutative linear logic. Okay? So what we're going to look at is a minimal kind of system, which I call L plus epsilon. In the fragment, there's a miniature fragment that has only left division, additive conjunction, and multiplicative unit, okay, which captures the following principles, which are true in L models. A times 1 equals to 1 times A, and 1 times 1 equals 1. Okay, so I insist that this is only in this small fragment. All right, and so here's the sequent calculus presentation of this small fragment. And the theorem is that any system which includes this and is L sound is undecidable. Okay, in particular, so is the set of all L true sequence. However, a big caveat here, I want you to keep that in mind. We do not know whether this set is RE. Okay, so it could be worse than just undecidability. Okay, so let's give a proof sketch of this. What we're going to do is encode two counter machines. The direction from computations to derivations is established by constructing the corresponding proofs in the small fragment, and a backward direction is done very cleverly by using L models. Okay. Now, to encode the Minsky machines, I'm not going to do this in great detail, but just to give you a flavor, I'm going to need a special symbol B. Okay. Let's say if the machine is in state Li with C1 is K and C2 is K1 and C2 is K2, then it is encoded in the following way. Okay. So L denotes the state of the machine, and this denotes the state of the tape. Okay. And there are the beginning and end markers, and then just the repetition of this particular propositional symbol. Okay, and now we'll do something clever. Okay, in order to land into the miniature fragment, we're going to use something we call pseudo-double negation. Okay, so this is not negation, is that special symbol B. Okay, okay, F under B, the whole thing under B. Okay, and then the issue is to encode all the necessary commands of the two counter Minsky machine, okay, with zero checking, right, in the following way as the formulas of this fragment. I'm writing multiplication whereas I don't officially have it, but I'm allowed to do this because since it's on this side, I can represent this as nested implications. Okay. Okay, so all operations are encoded into a leading formula of the form 1 and G, where G is a big conjunction again, which includes the following kinds of formulas. Formula that we just saw briefly on the previous slide for each instruction of the Minsky machine. And again, each one of them is of the form beta under alpha to the BB. That's the pseudo-double negation. Okay. Things for atoms and things for terminating computations. So where L is 0 is the final state, and both counters are required to be 0. Okay. So now the basic lemma to be proved is that the sequent 1 and G comma delta yields B, where delta encodes the initial configuration machine, is derivable in the small calculus if and only if the machine reaches state L0 with 0 counters, starting from the initial configuration, if and only if. Right? So the one direction is from computations to derivations. You have to make sure that you can act. One of the things you have to make sure that you have to access the commands, because these things are, remember, lists, not sets or multisets. And this has to be proved that because of the form of our encoding, if I get delta 1, delta 2, it turns out be provable, then I can switch the delta 1 in this particular form, not in general. Okay, so this allows locating the commands near the necessary place in the configuration. There are several other technical details, but this is, and then to go backwards. Okay, we're going to use semantics. Okay, so if BM is the set of terminating strings, that is the codes of configurations of the Minsky machine, such that the machine reaches the terminating one starting from this configuration, we're going to use the following L interpretation. Okay, so if atom A is not that distinguished atom B, I'm just going to say that the assignment on A is singleton A. And if it is B, then it's all XYs, such that YX is in the terminating configuration, starting configuration, which leads to terminating configuration. And then you have to prove the lemmas that this, for instance, that if the encoding is derivable, then the interpretation of the antecedent is in W of B. Okay, my soundness theorem. And from this, I conclude that the configuration Li, K1, K2 terminates to L0, 0, 0. Okay, so this is for all L languages. Okay, now, here's an interesting twist. Regular languages. The class of regular languages, recall, is the minimal class, including the empty set, the singleton for the empty word, the singletons for any letter, and closed not just under language multiplication and union, but also under Kleene star. Okay, so that's the iteration. Okay, so as a specific class of L models that I'm now interested in includes only models in which all languages are regular. Okay, and let me call such models L-reg models. And now you have to check that this definition is consistent, because the class of regular languages is closed under those Lambek operations as I showed at the beginning. Okay. Without the unit constant, important caveat, without the unit constant, the fragment consisting of 2 divisions and conjunction is known to be complete with respect to regular models. This follows from the work of Bushkovsky and the work of Sorokin. So I'm going to get rid of one of the divisions, but I'm going to add 1, okay? And the situation completely changes. So we're going to use theories in language with the unit constant. And what you've just seen in a couple of slides ago, the theory of all L models in the language of left division, conjunction, and 1 is sigma 0, 1 hard. And let me just remind you again, we don't claim that it begins to sigma 0, 1. It could be harder. Somebody could work on this. Okay, nice problem. Okay. On the other hand, if you look at this carefully, the subclass of regular models belongs to Pi01 class. Why? We now have to quantify over regular languages, that is over regular expression, and this leads an arithmetical universal quantifier. Okay, but you say, fine, that's one arithmetical universal quantifier. What about everything else underneath? Now you have to do a kind of a painstaking, careful analysis and show that whatever it is in the underneath in the definition of L interpretation is decidable. So you get one arithmetic quantifiers. Okay, and now since no sigma zero hard languages can belong to Pi01, we get the following wonderful theorem. The theories of L models and of L regular models in this fragment are different. Okay, and in fact, from our proofs, we can extract a stronger version. In other words, we actually find a sequent of this specific form so that A, we can construct an L model such that the sequent is not valid in the model, and B, the sequent is valid in any regular models. Okay. I think I was able to finish on time, so I thank you very much for your attention.
Questions? Oh, just what is the complexity of coupling negation?
That is a very interesting question. For some system, we just can do standard cut elimination. And for some other versions, we need to do a sort of a inner cut elimination first, and that one is more complex. But the standard one is just a standard approach. Okay. I wanted to say, since you raised the issue of complexity, I wanted to say a few things about the complexity of the calculus. And there's a difference here in commutative case and non-commutative case. So in commutative case, you actually get NP completeness if you just have one left division. Okay. Whereas in the non-commutative case, this is in polynomial time. This is a result of Sabatier. We can show that if you now add conjunction, so just two connectives, this is becoming polynomial space complete. Or if you add only disjunction, then it already becomes p-space complete. This is inherited in the commutative case from the non-commutative case. Okay. An interesting remark here, and maybe I get to talk about this next year or some other year, is that in fact these results hold even if I have only one variable. Okay. So non-commutative case is p-space complete for the miniature fragment of one variable left division and conjunction.